welcome to the Samuel Stevenson podcast. Today I have with me a man with a superpower. He can not only fly, but he can explain to you in detail how to fly. He's an aerospace engineer, and his passion for aviation is simply something he cannot contain. Welcome, Mr. Kumar. How are you doing today, man?
Good. How are you?
I'm doing great, staying busy as always. So, could you tell me a little bit? I've seen some plane flying stuff going on with you. How long have you been flying? When did you get into that?
Oh, I've been flying since 2015, 2016. So whatever the math is, 8 years, roughly 8 years. But I've known I was gonna I've been in love with aviation since I was 3 years old. Like I remember when I was 4 years old, like when I was the first time I flew was when I was 3 years old. And when I was 4 years old, I told my mom, like, I was like, well, I'm gonna design airplanes when I grow up. Um, so that's what I do now. I design airplanes.
Holy cow.
Yeah.
So
Ah,
you were
awesome.
flying when you were three. Were your hands on the controls? Like, how would you explain that?
When I was 3 years old, no,
Yeah.
no. So that was the first time I flew, as in that's the first time I got in an airplane. Because
Okay.
I remember going to the airport. I remember like the security check. I remember watching out from the window, and just being fascinated by the whole thing. And then my parents saw that I was really interested into it, so they bought me a bunch of books, and it just like spiraled all out of control. Personally, I've been a pilot since 2015, 2016. So it's 8 years, 7, 8 years. I've been flying that long. But yeah, I've been designing airplanes since six years or so, since I've been getting paid to design airplanes.
Okay. Awesome. So when you're does when you're a pilot, does it make you a better pilot being an aerospace engineer?
It makes you a worse pilot. It doesn't
Uh-oh.
it doesn't make you a better pilot. It actually makes you worse
Okay,
because
tell me.
flying an airplane, if you're a pilot, your job is to operate a machine, right? You need to be constrained by the manual of how the machine has to be flown. A manual that's been written by hours and hours of flight tests by multiple engineers spending millions of dollars assessing and evaluating the performance of. When you're an engineer, you start thinking you're smart. You start thinking, oh, if I
Oh.
want to slow the airplane down, I'm not just gonna do the obvious steps that any normal pilot does. I'll dump the flaps because that's going to increase my drag. This is something I've done. This is a stupid mistake I've done. And my CFI at that time, my instructor, he looked at me. He's like, "Why would you do that?" I was like, "Oh, because I'm increasing the CD because of the induced drag." He's like,
Uh-huh.
no, what about the change in the pitching moment? Like there's certain things, like being an aerospace engineer makes you a worse pilot,
Hmm.
my personal opinion. Because operating a vehicle, like, you want to be within the constraints that have been defined by the engineers. If you start thinking like an engineer, you'll start going outside the constraints, start becoming unsafe.
Got it. So there's a lot of so it sounds like there's a lot of because I haven't flown myself aside from being in a plane. There's a lot of like time spent making sure that this particular type of plane is flown this way, step
Yes,
by step. Okay.
yes, yes. So whenever you design an airplane, you design it, you go through PDR, CDR, you go through design reviews, you go to iterative design reviews, you go through complete design reviews. So after a complete design review, you actually build what you designed, right? So you build it and then you test it. You test to make sure, one, you built the right thing, you built what you wanted to build, the performance is what you expect it to be, and it flies the way it's designed to be flown. So you assess all those things through flight test, through variety of testing, and the top of that is flight test. And once you flight test, then there's a bunch of engineers whose whole job is to write down how the airplane is supposed to be operated. And me being my specific specialty being in flight controls, guidance, navigation, control systems, is we constrain the flight computer to be within a happy place, right? And doing that is we do a bunch of testing to keep the computer in a happy place. So that's what we do when we design the airplane, and that's how we write, or other people, they write flight manuals. They write, hey, this is how the plane's supposed to fly. And my job is to make sure we constrain it into a nice place where the plane can fly, if that makes sense. I know it's kind of kind of a weird description of
Yeah,
what we.
it does make sense. Could you be a little more descriptive on like what the flight computer is doing
Yeah.
compared to like what someone's like manual control versus like autopilot
Yeah,
stuff
yeah, yeah,
is?
yeah. Oh, this is fantastic question. Fantastic question. So, okay, let me see what's the best way to explain this. So, have you ever driven a really old car, like 20 years old?
Yeah, it's called high school. Yeah,
Yeah, yeah. Like, was it stick shift?
it was.
Okay, cool, 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 perfect. So, remember that car? That car, when you press on the gas, you're actually directly increasing the fuel flow going in the engine. If it's fuel injected versus if it's carbureted, slightly different, but there's no computer in the process. That's not true today. Today's
Okay.
cars are basically computers,
Okay.
right? Even if it's not a Tesla, any car will have an ECU, an engine control unit, right? So your inputs are going to a computer, and the computer is actually making the decisions on what to do. Same thing in an airplane. What we want the pilot to do is we want the pilot to tell the airplane what the pilot wants it to do. And the airplane has to move the controls, so move the wings, move the elevators, move the ailerons, move the spoilers, do whatever it needs to do to meet the pilot's demand. That's the job of the flight computer. So right now, and this is slightly different in a car because when you move the steering wheel, you're actually moving the tires. Like you can go out and watch the tires. But in an airplane, and typically that's also true for most airplanes, but the scheduling and the planning of how to move the surface is all controlled by a computer.
Okay.
So you tell the computer that I want to move 10 degrees to the right, and the computer will move the surfaces what it needs to do to achieve that rate of turn to get you 10 degrees to the right. And that would be like a state-of-the-art airplane, right? A state-of-the-art airplane would fly that way. Future airplanes, and there's certain military airplanes that do this, and there's certain airplanes under development that do this, where we take away much more control from the pilot, where we actually tell the pilot to just point the airplane and the computer will fly the airplane over there. This is completely different from an autopilot, right? Most
Okay.
people would realize that autopilot is kind of like cruise control on a car, right? You don't need the cruise control to drive the car. There's still a computer that's converting your gas input, your brake input into actual commands to the car.
Hmm.
But you can put cruise control on and just monitor the airplane and just monitor the car and chill. So an autopilot is just cruise control. That's what it is.
Okay.
Uh, you don't. A flight computer is much more than just an autopilot. An autopilot is basically cruise control. A flight computer is basic functions.
Okay. So how does that relate to like automation compared to like AI? Is that like borderline getting to the point where
No, no. So AI is AI is a complete different beast,
okay.
right? And in my personal opinion, AI getting into actual primary flight control functions. So there's primary control functions, which are like the highest integrity. That means they're the most robust system in the airplane. AI getting into PFC, primary flight control systems, is way, way, way far out. Like
Okay.
it's not, you can't just put Chat GPT, like Chat GPT fly the airplane. That's just not gonna happen. Sure, there might be like some military or R&D guys that might test something out. DARPA has been doing some testing, right? But you're not gonna go to Southwest and they're gonna have an airplane that flies on AI. Like this is not happening for a while.
Okay.
And the main reason is the issue with AI is determinism. It's very important for the flight critical functions to be extremely, extremely, extremely deterministic. That means that for the same amount of inputs, the output is always the same, always. There's no gray area whether the output's same or not. So all of this automation is none of this automation is artificial intelligence. This is all basically just computer code and smart algorithms.
Okay.
Very deterministic, very clear algorithms. So I'll give you the simplest one. and this is very similar to a car. You're driving a car. It's kind of like power steering, but not really. So you know how when you go fast on a car, you need to move your steering wheel just a little bit to
Sure.
turn a lot, versus when you go slow, you have to move your steering wheel a lot, right?
Right.
Imagine if you always move your steering wheel the same amount and the rate of the turn of the car changes with the speed.
Oh
So
man.
that's called gain scheduling, and that's
Okay.
we do that in airplanes. So in an airplane, the flight computer will, and not all airplanes, certain airplanes, right? Like the older airplanes, some airplanes don't have flight computers. The newer airplanes, like the last 20, 25 years, well, actually no, since 70s, so 50 years, they've all had flight computers, right? So so essentially you gain schedule the controls. So if I'm going slow, I don't need to turn too much, or I don't need to pull too much. I need to pull the same amount, and the computer will actually move the surface much more to get the same turn. But I need to, my strategy for flying the airplane remains the same. My
Okay.
strategy for turning the car remains the same. So that's an example of automation, right? We call it gain scheduling. That's the very simplest example, to all the way to state of the art where we do NDI, nonlinear dynamic inversion, where we invert dynamics of the airplane. It's just much more complicated to explain. But the simplest example is like a gain schedule.
Okay. So when I would imagine bouncing back and forth between like gain schedule versus not, it'd be very difficult to get adjusted to the mechanical controls.
Yes, yes, you would not bounce. You would not bounce on and off. You would have the gain schedule always on. It's just at some point the gain will be zero, right? At some
Okay.
point it'll have no impact. So if you want, let's say a car is a perfect example, right? But planes are very similar in control methodology. So let's say a car has a minimum speed of 0, right, and a maximum speed of 100. And I know that's not true, but let's say it's 0 to 100 miles an hour, right?
Sure.
And the midpoint is like 50 miles an hour. And you say, hey, 50 miles an hour is the sweet spot. I want to design the car for 50 miles an hour.
Mm,
And if you design the steering wheel you want always, if you move the steering wheel 10 degrees, you want the rate of turn to get at 50 miles an hour at every speed. You have a higher gain at the higher speed, and you have a lower gain at the lower speed, right? So
okay.
the amount of multiplication that's happening to your input is changing. That's all it is. That's all gain scheduling is. So it's always on. It's never being turned off, because turning it on and off would actually confuse the pilot. It will, or the driver.
Okay. Right. So that would make sense. So is it sort of similar to like, I guess the closest parallel I can make is car like racing, where having mechanical feedback from the wheels all the way back to your steering wheel is extremely important to like feel what
Yeah.
you're doing. Is that
Yeah.
the same in a plane?
Yeah, that's such a good question. That is a really good question. It's been the cause of multiple accidents. We call it biodynamic feedback.
Okay.
So getting feedback back to the pilot, is it just as important? This is a very contested point. So my personal opinion is, depending on the level of augmentation of response type, as in
Oh man.
depending on the level of automation, it becomes less and less important. If the level of automation is very low, it's extremely important.
Okay.
When I fly an airplane, my airplane is completely mechanical. There's no flight computers on it. The most electronically advanced thing on my airplane is a radio. My instruments are, well, actually, one of them is electric now, but most of my instruments are like, they're analog instruments, except for
Okay.
one. They're analog instruments. And the one is because I'm trying to go fancy, but
Sure.
excuse me. But because my airplane's from the 60s, excuse me, my airplane's from the 60s, it's really old. So for me to feel the feedback is extremely crucial. Without the feedback, I would die. I cannot land an airplane without the feedback. I probably cannot take off an airplane. Well, I probably can take off an airplane, but I probably can't land an airplane without the feedback.
Okay.
Probably it would be hard to do basic maneuvers without feedback. So the mechanical feedback is critical. However, with the higher levels of automation, we're changing the response type. So we're doing stuff like gain scheduling. where the response of the airplane is very, very predictable. So the feedback is not that important. So depending on the level of automation, feedback becomes more or less important. But there's so many tricky things with feedback, especially in airplanes, that we don't get in cars. So for example, the airplane vibrations can go back through the pilot, back to the airplane and grow. So let's say an airplane's vibrating. So the pilot's vibrating, the pilot's
geez,
vibrating. So the pilot can end up reinforcing the vibration, causing it to grow.
Yeah.
It's called biodynamic feed through, which has caused multiple accidents in the past. So those concerns are still there.
How do you avoid that? You just like let go?
Well, yes. So this is a good question. So for lower frequency stuff, if you realize what you're doing, you let go. For higher frequency structural mode interactions, it's just too fast for you to let go. Like you'll damage the airplane before you let go. So you design the stick, the inceptor, and we call it the PVC, the pilot vehicle system. You design it to dampen out any frequencies. So basically you design the stiffness in the stick and the damping in the stick, and you couple that with the control law and the dynamics of the airplane. You analyze it to make sure that for any situation, the oscillations are well damped. And we do a bunch of things. The whole idea of designing control law is actually just dealing with all the stuff. It's never just performance. It's performance, safety, reducing oscillations, everything. So you shape the performance of the airplane through software, so how you control the airplane, and the hardware through the stiffness in the stick and the damping in the stick, to reduce the probability of biodynamic feed through happening.
Wow. So what you're saying is, like, because I saw a guy on YouTube like make his own little plane out of like foam and stuff, and he flew it. And of course, he seemed like an engineer, had a big
Was he
crew
sitting
behind
in
him.
the airplane?
What's up?
Was he
Yeah.
sitting in the airplane, or
Yeah,
was
he flew it. Yeah,
Okay,
he got like 4 electric motors.
Yeah.
Anyway, so he did that, and I was like, oh well, maybe it's not that hard to just like make an airplane, but apparently it is.
No, it's really hard. So it depends. So that airplane is an experimental airplane, which will have a decent performance for a very small payload, basically for the pilot himself.
Okay.
Or very small flight envelope. We don't design airplanes like that, right? Like we design airplanes to be stable and robust over a variety of operating conditions.
Okay.
That's number one. Number two, when it comes to certifying an airplane for civilian use or even for military use, right? Not an experimental stuff, right? You could put together an airplane, fly, and go kill yourself, and no one will care, right? Because it's your hobby, right? You
Right.
get a license from the FAA. Very easy to get experimental licenses. You get an experimental license. Okay, cool. I'm gonna go fly this, and it might not be safe. Like the FAA doesn't. Of course, the FAA looks for basic level of safety, but it's not the same level of compliance that goes into certifying an airplane for civilian use.
Okay.
To certify an airplane for civilian use, the probability of a catastrophic accident is, like, for example, like a 737 or 757, like a Boeing plane or an Airbus plane. The probability of a catastrophic failure is 10 to the power of -9. Per 1 in 10 to the power of 9 flight hours. So 10 to the power of 9 is 100 billion.
Okay.
So they expect the probability of one failure causing the airplane to catastrophically fail is once every 100 billion operating flight hours, which is insane. So it's 100 billion, 1 billion, 10 to the power of 9, whatever that is.
Okay.
But the level of design assurance that goes to meet that probability is insane. So yeah, they're pretty hard to design.
Is that like related to, okay, so I went to college for manufacturing engineering, and one of the things I learned about was non-destructive testing. And the teacher was in the aerospace industry for Boeing forever, and just wouldn't stop talking about like taking apart planes and inspecting everything. Is that schedule related to like that flight hour risk in that they?
So no, that's a good question. The assurance level is based on, so what you talk about is reliability. Okay. And sure, there's some assurance, like the assurance is basically like system level design. Is your system robust enough to deal with it should be robust enough to deal with single failures like that, right? It should be robust enough to have a low probability of catastrophic failures. There should be enough redundancy and fall through mechanisms. With hardware, you're dealing a lot with reliability, right? Like how often do you need to do changes? So, for example, you could have a part in an airplane which needs to be changed every 100 hours. The operating manual tells you, hey, every 100 hours of operation, you need to change this, let's say, propeller. I'm just making stuff up. Every 100 hours. By the way, this would be a terrible design. But let's say the design says that you did the design, you build this propeller, amazing propeller, you did NDI, non-destructive testing, and you realized, the airplane tends to the propeller tends to get fatigued every 200 hours. Like it starts to get worn down, and you do NDI and you figure out, oh, it's starting to get bad. And you realize it happens at an average, starts happening at 200 hours of flight time. So you could go build an airplane like, hey, you know what? If this part gets bad every 200 hours, I'm just going to put an operating restriction in the flight manual that says this part has to be changed every 100 hours of operation and ship it. And that will be perfectly fine, perfectly fine. It will be pretty expensive because you have to change a part every 100 hours.
Sure.
Right. And you could prove that the airplane is robust to not have a catastrophic failure in 1 billion flight hours because you put a restriction that, hey, every 100 hours of flight time as an owner and as a pilot, it's your job to change this part.
Oh,
If we don't change
wow.
the part, then if you change the part, you install it correctly, then we guarantee the airplane's safe. But the part has to be changed every 100 hours, right? So it's still
Okay.
a safe airplane. It's just like cumbersome that you got to change it every 100 hours, or you gotta spend the money to do that.
Okay,
Um,
so that like super low percentage or probability of failure is tied to all of those rules and specifications for how this
yeah,
thing's designed to
there's
be.
it does. That's not really my specialty, but it does involve like mean time between failures, MTBFs, in that calculation, I believe, but mostly MTBFs, like what you talk about non-destructive testing and finding when things fail, hardware side, those are typically for reliability, right?
Okay.
And reliability is not necessarily for safety. To some degree, if the part's completely irreliable, of course it's unsafe, right? But it's mostly like cost and efficiency. So if a part has the same safety design, has the same redundancy, but it's reliable to only 100 hours of operation versus 10,000 hours of operation, then obviously the 10,000 hours of operation part, they're both the same safe, but the 10,000 hours of operation is just cheaper because you don't have to change the part every 100 hours. So yeah, it's slightly nuanced definitions.
Okay. Got it. So slight change of topic here. Um, I noticed there were some like you had been involved in some things in the past regarding like I don't know if it was research related or what, but like sound and vibration,
Mhm.
sound absorption,
Oh yeah,
acoustical stuff like that.
yeah.
So I saw one of the things pop up that uh inside for all of the stuff that I did learn about the actual turbines and jet engines, I did not know that there was a like sound suppressing
Oh yeah,
layer
acoustic line.
inside
Yeah.
acoustic liners. Right, right. Okay, so are you somewhat brushed up on that topic? You could
Oh
talk
yeah,
about it.
yeah. So my research, and this was 6 years, 7 years ago now. That was when I was in grad school. I did two specific. So I studied aeroacoustics in grad school. So in undergrad, I studied. I was. It's so funny. I've done all of this, and now I'm doing controls.
Right.
But in undergrad, my passion was aerodynamics, and in grad school, it was aeroacoustics. Um, and over time, I realized like the most interesting problem to solve is actually guidance, navigation, control, which is what I do for a living, even though I didn't do any research on that in grad school. But anyways, so we talk about acoustic liners. Without acoustic liners, the engine won't work. They
Why
not just
not? How
dampen
does that?
sound, they dampen vibration.
Oh,
It would be
okay.
so loud, it would most likely there might be some resonant modes that would cause the engine to blow up.
Wow.
Mostly, we concern ourselves with the suppression of sound. And now engines, like turbine engines, have a very characteristic noise profile where you have a peak in amplitude at what we call the blade passing frequency and its harmonics. So blade
Okay.
passing frequency is directly related to the RPM of the fan inside the motor.
Okay.
So if you ever notice, if you have like a ceiling fan, the faster it goes, the nature of the sound changes. It becomes more high pitch. The
Okay.
faster it rotates versus the slower it rotates, it becomes lower pitch. So that's the peak in the sound. And that peak in the sound hurts the most. There's also a broadband component, which is just the combustion, right? There's all this combustion happening in the engine, the explosions. Those are much more broadband, right? Suppressing those is a different story. But
Okay.
the peak of the sound, which happens because of the fan moving, that is easier to suppress. So what we do is we design these things called liners around the engine, which basically they're like quarter wavelength resonators is what we call them. They're designed for specific wavelength, and they suppress the noise at that wavelength. So that wavelength corresponds to 1 RPM. And what engine manufacturers do is they design the liners for the cruise RPM, cruise N1 setting of the fan. So cruise RPM setting, they design the liners for that. It might be, well, I'm not really sure about that actually. They might do it either for cruise or for landing. There's different phases of flight.
Right.
So it depends on the engine manufacturer. I think Pratt and Whitney does it slightly differently. But anyways, the issue is that any engine, right, even your car engine, doesn't operate at 1 RPM. It operates at multiple RPMs,
Sure.
right? Depending on how much load you have on the engine. Same with an airplane engine, right? In cruise, it's probably going to remain constant because nothing's happening, right?
Right.
So just cruising, chilling, but approach, descent, takeoff, landing, you're changing RPMs, right? You're changing your thrust, so you're changing the RPM.
Mhm.
So that means your noise profile is continuously changing. The acoustic liners cannot deal with that because they're designed for one wavelength, for one
Right.
RPM. What I did was I designed a liner where you could change the range of optimized RPM by a little bit.
And you did that by like shifting the
Yeah.
circle things, right? Okay. Like changing the like shape of the
Yeah. So
okay.
this was actually a really cool. We published a couple of papers on this. We basically just changed the shape of the resonator, which changes the mass damping. So it allows you to have a slightly broader response. So it
Okay.
makes the resonator, it makes it less efficient, but at least it works over wider range, right? So yeah, that's the work we did over there. And we had a couple of engine manufacturers look at this. Their whole issue was the added weight.
Okay. I was gonna ask, was it worth doing?
Yeah.
Oh,
So that's the tricky question, right? Like for the amount of performance we were getting, the added complexity of the weight and the added complexity in the engine was not worth it.
okay.
But it also depends on different markets. So for example, in London, someone would say, yes, it's worth it, right? And in the future, I expect there to be much more noise related ordinances where you're like, hey, we need much better noise suppression. Also, I see multiple variations of the research work I did to improve the performance to reduce noise. But there's a very important reason why I never went down that path to either commercialize the idea or to do a PhD on that. And I just don't think uh, that improvement in itself is what I would call like a 0 to 1 change. Right? Are you aware of the concept of a 0 to 1 change?
Not particularly. Do explain it.
Yeah, with me. So Peter Thiel wrote this book called 0 to 1. And Thiel Fellowship was one of the first investors. Well, they weren't technically direct investors, but they gave money for my first startup venture when I was 18. So I'm a big fan of Peter Thiel, right? Because who believes in like an 18-year-old from like a third world country? So, so his book, 0 to 1, the idea is it's very hard to take something from 0 to 1 and it's easier to take something from 1 to 100. So it's very hard to come up with something new and create such a change that's a step change.
Okay.
But it's easier to scale a step change to the rest of the world or to a bigger market. Now, of course, manufacturing engineers will disagree to that. Manufacturing sucks. Like, dude, what are you talking about? Like, scaling is the hard part because then money and everything comes in, right? But the idea is like the R&D of building something that's a 10x improvement, that it's like from 0 all the way to 1, from nothing to something, is much harder than scaling something that exists that works to 1 to 100. So for me, when I got into the aerospace industry, initially I was just excited to be there, right? I was just excited. Oh, this is cool. I'm doing what I always wanted to do. I made it. This is awesome. And then over time, I realized that a lot of innovation in the industry is not driven from a 0 to 1 change. We're not really trying to do something big. We're just trying to make small incremental changes. We're like iPhone. We're like, you change a port and you charge $1,000 for the new iPhone, right? And of course, you put in, oh, I have new silicon, I have new processor. But really, let's be honest, the change is not that much.
Yeah, right.
iPhone 14 and 15, right? It's not like a huge step in innovation. I'm not saying that's bad business. That's the reason there's no change in innovation is because companies reach this place of monopoly or duopoly where they don't feel the need to compete, and that stifles innovation. But for me, that project specifically, I did not think that was a 0 to 1 change. Like, it wasn't going to dramatically change lives or dramatically change the bottom line of a company or dramatically change the life of a pilot or the life of a civilian who's traveling or life of a service member who's flying a military jet in Afghanistan. Like, it wasn't going to make that huge of a difference. So my goal with my passion projects is typically to try to work on 0 to 1 step changes. I don't think it's the best way to make money. I think the best way to make money is to work on 1 to 100. But things I'm passionate about, I like to work on ideas that go 0 to 1.
Like what? Could you give one example?
Yeah. So the current company I'm part of, we're building electric vertical takeoff and landing airplanes. So building airplanes that take off like a helicopter and fly like an airplane. They're fully electric. They are single fault tolerant. That means you could have like one engine fail and the airplane will be fine. And they're fully electric, so there are no emissions, and the sound profile is amazing. The acoustic profile acoustics was one of the main design constraints in the design of the airplane. So that's a 0 to 1 change. Like, when we get into service, it will be something people have never seen before. Even now, when my friends or like partner, like a girlfriend, like if she comes with me to on site, I work remotely now, but they would just be shocked. Like, what is this? Well, that's the future. Like, that to me is 0 to 1 change. Like, when you build something that doesn't exist, that solve a problem that does meet a niche, but it's such a big change that no one expected that to happen, right? It's not like you're scaling, making incremental change. So that's what I would call 0 to 1 change. In aviation specifically, bringing autonomy will be a 0 to 1 change when that happens. Using other kinds of fuels is a 0 to 1 change. So to me, those things are 0 to 1 change.
Okay. So yeah, I saw the air acoustics thing that you were doing, and I was poking around through like a Joby or however it's pronounced, and
yeah,
I saw the like all these claims on like acoustics, and I was like, this guy, he's got to be behind this whole thing because he was studying here.
Well, actually, I did not work on the acoustics of the Joby airplane.
Okay.
Actually, the team who worked on that, and one of the main members was Alex Stoll. Alex designed the airplane, and back in, I think he started working 2012. So he worked on it a long time. Alex was the first person in the company. Unfortunately, Alex passed away 6 months ago in Feb. He passed away in a car accident. He was 38. So right now we always say like this is for Alex. Like, we're gonna finish his job.
Yeah.
But he I'm not going to give him all the credit. There's other people on the team, of course, that worked on the acoustics, but I actually did not work on the acoustics of this airplane. When I joined the company, I moved, like I said, I moved into guidance, navigation, control, those areas of study, because I just find them very, very fascinating now. There was a time when I was very into aeroacoustics. Now, not so much.
Okay.
Yeah.
So one of the things I saw was that like partnering up with Uber and everything. And I was just thinking to myself, what I was not expecting was to open my Uber app and be like, oh, flying is now an option. Like,
Yeah.
what is that? What is that market they're trying to hit? Because like regular people aren't going to be flying around in air taxis. So,
Yeah. So I'm not going to talk on the business development aspects, right?
okay.
I get
Yeah.
a lot of questions from people on like what's the cost per price mile and stuff like that, right? And the reason I can't comment on that is, one, like it's not my area of expertise, right?
Okay.
We're no longer a small company. Now we're like, we have big teams. The company's grown 10x since I joined. 10x.
Wow.
It's not like it's doubled, it's 10x.
Yeah. And that means your value has 10x with it.
So, well, that means like one in every like 1 in 10 people are the only people I know from
Right.
like days, right? And like now the
Right.
company's grown so much. In fact, my team, I'm almost the most senior, as in longest been in the company member. No, I think Omid, yeah, he's been there longer than me. But yeah, it's so in terms of business development, also it's a public company, right? So the numbers are all like what numbers are given to investor relations. But yeah, like I hear that argument a lot, and the biggest thing I can say is it's all about scale, right? Any network service like Uber, for example, Uber's cost came down with scale. That's the way Uber got successful. If you remember when Uber started, it was Uber Black,
Okay.
right? It's like they would have like this fancy car with a chauffeur and all that stuff. It was expensive. But as they got to scale and network effects started happening, the cost went down. So I think scale will be huge. The other advantage our company has is we're fully vertically integrated. So we can control cost at every stage of the development process. This is not necessarily true for Uber,
Okay.
because Uber essentially, they don't own the cars, they don't own the drivers. They basically just connect stuff. So they can't control costs over the operation that well. I don't want to speak for Uber, but I'm guessing.
Sure.
So first principle would tell you. But in a fully vertically integrated environment, and we plan on operating our own airplanes. Like we plan on doing the operations as well. We actually are Part 135 certified. Like we're certified to do operations now. But the with the fully vertically integrated system, it helps you keep, it's, in theory, like the idea behind it is like it helps you understand where your cost centers lie and how you can bring down the cost, and where you're actually investing and what your actual margins in the business are. um so I, from my personal opinion, we're pretty well set up when that time comes to make those assessments.
Okay. Man. So, okay. Yeah. So when you say vertically, when the first time you said vertically integrated, I was like, oh, okay. So your planes, they go up and down.
No, but what I mean by, I mean, the planes do that.
I
They're
hope so.
designed to do that. But vertically integrated is like the R&D is in-house, all the production's in-house. There's no, typically, most aviation companies, like a company like Boeing and Airbus, they design the airplane, but a lot of the components are built by other companies, right? So they send requirements out to other companies and they build the components. For us, almost everything has been built in-house, which has
Wow.
its challenges,
Yeah.
from a business perspective and also development perspective. But um, the company leadership made that decision a while back to be vertically integrated, and I personally think that's going to pay off.
Yeah.
But that's not typical in the aerospace industry. typically there's multiple small component manufacturers who build components. Like Boeing basically just builds the airframe and
Okay.
designs the airframe and integrates everything. All the flight computers, the control software, the actuators, the actuation systems, they're all being built all over the world,
Okay.
all over the country, probably not all over the world, but yeah.
Okay. So I saw that in one of your podcasts you had mentioned that as a kid you saw like that the best days in like people were saying, well, no, like this is aerospace industry. Like, how could it get better than this?
Yeah.
And you were like, no, 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 guys, listen up. It's gonna get better. And that's partially why you were so interested in it. So like, you know,
Yeah.
right now, having what we have, could you even imagine what we're gonna have 30 years from now?
Yeah. Oh, I think we're gonna build the future. We're not just gonna imagine, we're gonna decide what we're gonna do and we're gonna do it.
Yeah.
Um, a lot of people say, and I believe, those are the days that inspired me. Um, the Apollo program, the Mercury Gemini program, the Apollo program, they inspired me to this date, right? Like right behind me, that's translunar injection from Apollo 13 and from Apollo 11, sorry. But those those were that decade, the 60s was a time when the entire country got together to go after this really, really audacious goal to put a man on the moon. And ever since then, our sense of adventure has not been at the same level.
Mm.
Our desire to spend the money on something like that has not been the same level. And the funny thing is, a lot of people don't see the value in space exploration because it doesn't affect their daily lives. Or in
Right.
aerospace, right? They don't see the value. But the funny thing is, the amount of ancillary and auxiliary technologies that come out of these developments actually go to normal day-to-day life. MRI machines came from NASA.
Okay.
So that's just one example at the top of my head. But not only that, but the amount of people it inspires to go be doctors, engineers, and go into STEM majors is insane. There was some research on that just came out in the 90s, which was pretty amazing. I don't remember exactly what it was, but I know the numbers shocked me. But the idea that our best days are done, that now NASA is just a lame duck who hasn't gone outside the low Earth orbit with humans for a long time is true. That is true. Except now, for the first time ever, we have commercial companies in the aerospace business. We have in the space, in space, at least in space travel, right? Aerospace, we've had commercial companies for a while. And these companies are led by really visionary people who really want to change the status quo. They see a market here. And because they're led by capitalism, they know where to cut costs while maintaining the safety standards.
Mm.
There's no cost plus programs. Well, you get a contract and you perform. It's just like normal programs now. And like space programs is just like a normal contract now, where's the cost plus contract that the Department of Defense would give out. But going back to the point, I think we're at a point where one, commercial access to aerospace has really opened up, especially in the space industry. Second, there's a confluence of technologies that never existed before that's going to enable a lot of this development.
True.
And that's specifically the fact that electronics are getting so cheaper, and we can use carbon composites in aerospace, and we have high battery energy density that enables us to fly. That's on the aviation side.
Right.
Before now, this was impossible. 10 years ago, if it come to me like, hey, we're gonna have an electric flying airplane, I'm like, yeah, dude, what are you talking about? Like, you're not gonna get the energy density to
Right.
fly an airplane. Like, your batteries are gonna weigh too much. But that's not true anymore. Why? We've been flying for 6 years. A full-scale airplane for 6 years. It's electric. Whenever people tell me, hey, electric airplanes, like, it's just not gonna work, it's like, dude, we've been flying it. There's a video on YouTube. We flew 150 miles.
Yeah.
150 miles. We said the range was 150. We showed it's on ADS-B. You can go look up on flight radar and you can see 150 miles. This is now we have the technology, we have the confidence of technologies. And also, the other thing I mentioned, the cost of electronics is getting cheaper, which is critical because the most high performing airplanes are unstable. So so an airplane design that would perform really well, be very efficient, is actually unstable. So if a pilot tries to fly an unstable airplane, he will crash it and die. They're inherently not safe. So
Okay.
so to build an airplane that's neutrally stable, or that's actually bare airframes unstable, but we stabilize the airplane through flight controls, that technology for the first time has gotten cheaper enough to actually put into civilian airplanes. So military airplanes have been unstable for a while, but military has a different budget, has a different, it's slightly
Yeah.
different. But to make they're not really looking to make money out of military airplanes, right? They blow billions of dollars. But to make something that's economical, now we have the enabling technologies. Going in the future, our biggest constraint in aviation. So for me, electric is important because of carbon emissions. In terms of mission, an airplane design that doesn't require a runway is very important just for accessibility. But going forward, our biggest constraint in the industry in terms of performance is actually pilots. Pilots are very expensive. So
Really?
fuel is the most expensive cost, but fuel is, that's operational expense. Like you can't get away without fuel. Like
Right.
even electric airplane, you got to charge it, right?
Yeah.
Like there's no free lunch. You're not gonna have like just like God blowing air on you, right?
Yeah. Yeah.
But a pilot, well, do we need two pilots? Can we get rid of one pilot? Can we get rid of both pilots? Like, can we take aeronautical decision making and move that to a computer? Can we take all kinds of aeronautical decision making and conflict management, all those things? Can we move that to a remote person who's controlling 10 airplanes? Like all those possibilities are are now possible for the first time ever in our history. And it's beautiful. Like the best airplanes ever are yet to come because the best airplanes ever might not look that amazing. Like people like me might not walk with their chest out, but yeah, dude, I'm a pilot. I fly an airplane because they won't need pilots. We'll take all their jobs. The idea is 20 years from now, I want to be in a world where we don't need pilots because we don't have enough pilots for how fast the industry is growing. One, two, honestly, I'm pretty sure we can take away from the role of a pilot. We can have computers do that. And I know a lot of people will be like, oh, that's unsafe, that's this and all that. But honestly, self-driving cars are much harder than self-flying airplanes. Much harder.
Really?
Yes, self-flying airplanes would be much, much easier.
Is that because you don't usually have like idiots flying around in the sky?
Also, yeah, you don't have a trash can, you don't have a stop sign, you don't have like a pedestrian walking, when you're flying an airplane.
Right.
Um, so fly, and also in a car, you have to handle with a lot of non-deterministic factors. You don't really have that in aviation, especially on what we call instrument flight rules, IFR flight plans. You basically on an IFR flight plan, which is how all airlines fly, by the way, when they fly with passengers, traffic separation, that means keep maintaining distance between airplanes and making sure airplanes don't collide. Traffic separation is provided by ATC. So now, of course, things still happen and pilots have a job to detect and avoid and all that. But you don't have that in cars, right? Like when you drive a car, there's no overarching person saying, I will make sure you don't collide with other cars. I will make
Yeah.
sure there's deconfliction. No, like the closest thing would be a traffic light, right? Traffic light would be the closest thing. It doesn't even compare to ATC.
Right.
IFR flight plan in the ATC is just like, well, I want you to turn right heading 210. The pilot's like, Roger, 210. The ATC saw on its radar, there's two planes coming close and told him, well, I want you to turn away. Right? You have that level of deconfliction. And then you have, on top of that, you have TCAS, which is like an automated deconfliction, which, hopefully people never have to use. But that takes another, and these things are in production. Like these are existent in airplanes. If you take a flight today, there's a TCAS system on it. Right? The future for us to make airplanes self-flying, way, way, way easier than for us to make cars self-driving. And we
Okay.
have self-driving cars. So I don't think that's too far out.
I'm
So
on
that
board with
I
that.
think that's why I think like our best years are yet to come. Like
Okay.
the best things, because I know all the new stuff that's happening in the industry, and it's mind blowing,
Yeah.
mind blowing.
So if you had like $5 trillion just set in your lap, where would you direct it, and like what would you do with that in terms of the industry?
So
Assuming you didn't want to like buy, Ethereum or something.
in the industry, if I have to spend the money on the industry, 5 trillion, we're going to Mars. As simple as that. Like there's
You
just
think?
there's nothing else I would do. Uh, because one, I want to, it will be fantastic. But two, I think it would inspire so many people to get into STEM, like the investment that you would put in,
Yeah.
much more than worth 5 trillion. Well, 5 trillion is actually a lot of money. It's like 25% of our GDP. So I don't know if they were totally that much, but let's say like a trillion, yeah, a trillion probably. Yeah, I think for us to be a multi-planetary species is critical. And again, for the first time ever, we have reusable rockets now. They've been flying for 8 years. Like we're getting there. And if Starship succeeds, that'll be the first fully reusable system ever. It runs on Methalox, so you don't have to clean the engines. There's no soot in the engines. They're absolutely fully reusable. It's like getting in a car. Like this future is coming,
Yeah.
and it's gonna put the Apollo program to shame. Like it's gonna be that amazing. And the funny thing is, it's not gonna be driven by Congress. It's not gonna be driven by some president. I personally feel the government's gotten much weaker, and with much less desire to take risks and to bet on long-term projects. But it's actually going to be entrepreneurs with that vision to actually make those leaps. It's going to be like smart engineers. Dude, there's like a rocket company starting every other day now.
Really?
Yeah, there's people with 3D printers building rockets, and they're flying them. Like there's fully 3D printed rockets that are being built, fully 3D printed. The engine's 3D printed. It's insane.
That is insane.
It is insane. Like the days of us looking up to NASA. I mean, I look up to NASA. NASA's amazing. They do amazing stuff. But that's not it. Like there's gonna be people who have that vision, and who've taken the money from other places, of their put together money to build the technology themselves and to do it. Like this is not just me saying and wishful thinking. This is happening right now.
Right.
So it's amazing.
Yeah, and there's been so much, like, especially in the manufacturing field, there's so much technology that's just like cheaper and cheaper, and now it's being like put in the hands of everyday people. And it's like these people are growing up with this stuff. You think
Yeah.
they're going to be super good at using it when they're 20.
Yeah. This is something that I've been noticing as I get older. I'm almost 30 now. But over the years I've started noticing this is I feel like the average person is getting dumber, but the people who are actually really forward thinking and smart, they're getting much more resourceful, much more. The average
Yeah.
person is like, whoa, is the earth really even flat? Is the earth, sorry, is the earth really even round? I think it's flat. It's like, I don't argue with them because I'm like, well, it's not worth it. Like, there's
Yeah.
no point. But there's people who believe the earth is flat, and then there's people like all these weird kind of beliefs, and they're consuming like STEM education. Our understanding of science and people's acceptance of science is actually reducing in the US. But the people who are into it, they're getting much more resourceful. So overall, I think we're gonna have much more revolutionary things in the future, just because of the number of people who believe in it, who want to do something, who want to make a difference. They're much more resourceful now. They have the internet, they have access to cheap money to try things out. And it's gonna be an amazing future, man. It's gonna be incredible.
Heck yeah. So last question for you. How do you plan to inspire the youth of today to get into aerospace just like you did?
Yeah. The biggest, so I've thought about this a lot. There's a macro and a micro. Okay.
Okay.
Macro level will be just doing more 0 to 1 things. more 0 to 1 things. So that will be building airplanes that, like, if we succeed, if our company succeeds, and we're gonna make sure it does. But if and when we're successful, our kids will grow up in a world which will be completely different than ours in just 5, 10 years.
Yeah.
Right. I mean, just imagine, like, 10, 15 years ago, there was no concept of Airbnb. There was no Uber. There was just taxi. There was no, I don't, Instagram. How old is Instagram? I don't know. 13 years old. Instagram is 13. There was no Instagram. There was no social media. It was a completely different world. Right. Same right now. I think with new technology, when people see, feel, and touch it, it will inspire them. It will inspire the next generation. So more 0 to 1 things will inspire. And I see that a lot with what SpaceX has done for people who are like 5, 6 years younger than me. They're getting into this the space industry just because they're inspired. Like, I've seen videos with people like crying watching Falcon 9 land.
Yeah.
And I'm like, okay, you know what? That guy, like, if he doesn't get distracted by some social media stuff about drop shipping or crypto, he's gonna go to school. He's going, you know what? I'm gonna be one of those guys. I'm gonna be one of those guys who's gonna build that system. Like, remember, the guidance system on the Falcon 9, which allows it to come back and land, was built by a human. Was
Yeah.
built by a team led by Lars Blackmore. That's his name. Like, that person and his team, of course, the team, it's always the team. They did this. A bunch of humans did that. A bunch of humans did what NASA and every space agency has been saying forever, that, oh, it's probably not profitable. It's probably, it's probably not worth the time. Well, they did it, and they reduced the launch of costs so low, and their reliability is still through the roof, even with reusability, that they're just milking money, and other companies are going out of business. Like, other
Yeah.
companies, and these guys just they're launching a rocket once every 3 days. They're gonna have 100 launches in 2023.
That's
I think
insane.
96 is what is going to end up being, but their goal was 100. 96 is close enough, man. But, like, that's insane. That's insanity. So things like that will inspire the next generation. That's the macro. Micro, I'm really concerned about the impact of distractions like consumption of too much social media, too much reels and TikToks, too much of our lack of trust in established institutions is causing a lot of people to have distrust in science. And on the micro scale, I really want to do something about STEM education for kids, especially underprivileged kids, lower middle class kids, or because I always look at, like, I come from a lower middle class family, right? Like, I come from not much. So when I have friends who were born in wealth, like, they just don't have that drive because they've lived a life of comfort. So unless they're very driven intrinsically, I personally think that the lower middle class people who really want to jump up and make a difference and really change their life, and also follow some passion because they're not in that state of comfort, helping them get STEM education will be critical. So this is something I've been talking to. There's a charity here called Inspire Kids. I want to teach kids, I want to teach young kids about science. So when they grow up and get on TikTok and have someone telling them how the earth is flat and how everyone's lying to them, and astrology is real, they don't believe it. Like, I think that's critical.
Yeah.
Those formative years, we're ruining them with wrong data, with freedom of speech, by putting anything we want in social media and people consuming that. We're actually, I think, ruining lives a little bit. I'm still not against it. Like, freedom of
Yeah.
speech, you post whatever you want,
Right.
but we need to provide people the skills to make informed decisions and use their judgment. And younger individuals from the age of like 10 to 17 might not really have that skill, right? They might just
Right.
absorb whatever they get. They might not have the skill to step back, like, well, is this really true? Is this fake?
Mhm.
Is this meme? Like, is that really meme true?
Yeah.
They might not have that skill yet.
Is Jada Pinkett Smith actually Will Smith? Is that real?
Yeah, that's the other thing. I love memes, man. Like I really enjoy them. They're funny, but God, like consumption of social media is so counterproductive. Like it takes away from deep work. It takes away from like sitting down and working deeply.
Yeah,
Um, and that's not like a thing for kids. That's for us grown-ups. Like that's something
sure.
I struggle with where I have to like, well, I'm deleting stuff from my phone. So it doesn't even come to mind. Nowadays, like right now, my phone, I keep my phone here, it's in my room. So so I don't even like touch it.
Good move. Awesome. Well, it sounds like you got a lot going. Your head's on straight, man. How's people are gonna find you? Plug yourself in here.
Oh, just look me up on LinkedIn or Instagram. Yeah, I can give you the links. You can drop both of them.
Yeah, I'll put them in the description.
Yeah, LinkedIn is basically for anyone, in the industry. I push a lot of content. Actually, I've slowed down in the last couple of months. We've had a pretty busy flight test campaign that I've been involved with as well. You might have seen stuff in the news. So, but I will get back to posting a lot more content on LinkedIn that's related to GNC, aerospace, all that stuff, and Instagram for anything and everything else. And I also have a website to look at some of the past research work I've done. I should go update that with some of the new stuff I've done. I should probably do
Yes.
that. But yeah.
Yes, indeed. Awesome. Well, thanks for coming on, man. This has been a great conversation. I've loved learn all this
Awesome.
stuff.
I appreciate it. This was pretty fun and some really good questions. I had to think about how to explain them. That's good.
Good. Challenge for everybody. I love it. All right. Well, that'll end the show. So thanks for watching.